11.7. Today we're going to take a look at cylindrical and spherical coordinates. Okay? So this is going to feel a lot like polar coordinates in 3 dimensions. But there's 2 ways of doing this in 3 dimensions, hence 2 types of coordinates we're going to be looking at. So the first one we're going to be looking at is probably the easiest to conceptualize, I'd say. This is the cylindrical coordinate system. So we have a point P represented by r theta z. R theta is the same as the polar representation that we're familiar with, right? So it's the distance from the origin for r, and then the theta is the angle measure from the positive x-axis. And then z is just the directed distance from that coordinate system up or down. Okay, so it's just like with cylinder, right? It just goes up or down from that coordinate system. So there's some formulas. These are going to look familiar, at least kind of familiar because we've seen ones like them. So the first one is x equals r cosine theta. You know that one. And y equals r sine theta. You know that one. And the last one's going to be your favorite. It's z equals z.
Nice.
Yeah. Rectangular to cylindrical also are going to look familiar. X squared plus y squared is r squared.
Oh, we lost you.
Oh my goodness. Okay.
That doesn't look like it's about to say things.
Tangent of theta equals y over x. And then that was the z equals z that you guys were talking about. Okay? Tangent of theta equals y over x. That gets us our angle measure. So we're going to do 4 of these where we convert back and forth. We're both going to be converting points and equations. Okay? So starting with points. So we have a point that's in cylindrical, and we want to move it into rectangular. So to go from cylindrical into rectangular, we're going to use those theta ones, right? So we're going to have x equals r cosine theta. We'll do y equals r sine theta. And then for free, we get the z. I mean, it's the same. So we don't have to do anything for that.
On homework, is it fine if we just go ahead and plug in?
Yes.
Okay.
That's what's in my notes. In fact, I just was writing it this one time. I probably won't write it again.
Dr. Chin would not like that.
I'm fine with that.
Just want to make sure.
All right. So R6, your theta, theta is negative pi over 4. So what is the cosine of negative pi over 4? Unit circle time.
Radical 2 over 2.
It is. Square root 2 over 2, and it's positive as well. So this simplifies then to what?
3 square root 2.
3 square root 2 it is. R sine theta, quite similar. So 6 sine of negative pi over 4. What's the sine of negative pi over 4?
Negative square root 0.
Right, that one's negative. So my y value is,
Negative 3 square root 2.
yep, negative 3 square root 2. And then, just like we had pointed out from before, z is z, so z is just going to stay the 2 that it already is. So my ordered triple is 3 square root of 2, negative 3 square root of 2, 2. Okay, so far so good? Let's go back the other direction. Rectangular into cylindrical. So rectangular into cylindrical uses the other sets of equations that we had. So x squared plus y squared equals r squared. So x squared is 3, so that's 3 squared. Y squared's also 3. Well, it's negative 3, but it's squared, so if you prefer, we'll do it that way, but negative 3 squared equals r squared. So I have 9 plus 9. So r squared is 18. I need to square root and simplify as I go. So what are my values for r, besides being plus or minus?
3 radical 2.
3 square root 2. So that's my r value. I have my z value. I get that one for free. I need my theta value, and I get that by using tangent of theta equals, and we need to have the y value, which is negative 3, over the x value is 3. So the tangent of theta is equal to negative 1. That's actually a unit circle value, but you're also welcome to do the inverse tangent if you prefer. So if you do theta is the inverse tangent of 1, what do you get?
You got negative pi over 4 there.
Yeah, it's negative pi over 4. It would also be 3 pi over 4. Remember that inverse trig functions have a domain that goes from, in the case of tangent and sine, they go from negative pi over 2 to pi over 2. In the case of cosine, it's from 0 to pi. So that's why you get that one. And then we have z equals z. So the z is equal to 7. And so we want to make sure we're in the right place, right? So think about the polar two-dimensional, which is easy enough to draw, because we've got multiple versions. I mean, even with the one that you had just said, right, this is also 3 pi over 4. We've got multiple pi values for theta and multiple values for r. We want to make sure we're in the right location. So in terms of an xy location, I'm at 3, negative 3, which means I'm down here, right? I'm in quadrant 4. So which of those r and theta combinations will work?
Positive with negative and negative with positive.
Okay, so the positive 3 square root 2 will work with the negative pi over 4 and the z value 7. Or if you wanted, you could do the negative 3 square root of 2, but then it would have to be with the positive 3 pi over 4 and the 7. So there's not just one right answer, which makes sense. This is polar. We're spinning around the circle, and so we've got multiple options. So either of those are perfectly fine. The first one's the one that I have written in my notes if you care, but either of these will be fine. Okay, so that's points. If we're working with equations instead of points, it works the same way. So for example, this one is rectangular into cylindrical, which is the same thing we just did a moment ago. So like the one right before it, it has z equals x squared plus y squared minus 11. So if I wanted to have it in cylindrical, I want to have it in r's and thetas. And that doesn't necessarily mean I have to have both. Just like if I had an equation in rectangular, it wouldn't have to have x's, y's, and z's. It could not have one of those and still be an equation in that plane, or in that surface, that space. So what do you see I could change in order to get this into the r theta form that I'm looking for?
Can you substitute?
Mhm.
Use X in the line.
Yeah. So what do you have in mind? Tell me what you're having in mind specifically, Adeline.
R squared cosine squared theta.
Okay, you could do that. There's an easier substitution though.
Just put in r squared for
Oh,
x
that's
plus
true.
y squared.
So sometimes there's more than one way to do it. There's often one way that's easier than the other. If you notice it, x squared plus y squared is r squared, so that is a very nice substitution. And in fact, we're done. Because in cylindrical, I have r's, thetas, and z's. I've got r's and theta, r's, z here. I don't have a theta, that's fine, but I'm finished. Notice the directions on number 4, they actually ask us to sketch it as well. So there's going to be a few places where they ask you to sketch something, but if they do, it's because it's going to turn into something that you're going to be able to work with in a familiar way, right? Like, ding ding, 11.6, read your bunch of pictures. That's what you're going to be looking for, okay? So first, we have an equation that's r equals 1/2 z, and we are wanting to turn it into rectangular coordinates. So I need the r to be replaced by something with x's or y's. What thoughts do you have?
Square root of X squared plus Y squared.
It's a good place to start. Square root of x squared plus y squared. So this is equaling 1/2 z. Now, technically, you're done in terms of like putting it into a form that's got all the right variables in it, but it's not very easy in this form to know what a graph's to be. So we want to change it around a little bit to get to the point where we can graph it nicely. So let's square it both sides first, yeah. So x squared plus y squared equals 1/4 z squared. And then I can move the z squared to the other side, because it's so far, if we go back and compare it to things in 11.6, it's not quite matching up just yet, but we're awfully close. So can you take a look back over there and see which one of the graphs we have that this matches?
It's an elliptic cone.
It's an elliptic cone, that's right. So this is an elliptic cone.
With the z-axis, right?
Yep, opening along the z-axis.
It's the one.
It's the one that we
You can actually
had to
draw
draw.
this one.
You can draw this one? You like this
Yeah,
one?
It's just this circle with the
Uh-huh.
thingy.
think it's
Thinner. It is cheating. You're right. It looks so nice, doesn't it?
Whoa, how did you do that?
I know.
I should start doing that on my homework.
Yeah, I thought elliptic cones.
Read out my ruler and make it precisely the same.
Did you? It's
No.
amazing.
We're getting
Okay.
closer.
I don't know. It's pretty close to that. Mine's not perfect either, but yeah, that's my elliptic cone. I should label at least the axes. That one's Z, Y, and
It
X.
looks really good.
Okay.
What's the one where it's just the one of them?
It's if we would have had just the top part, like if R is only, like if we only had the Z is positive only, but if you start out looking at the original equation, we don't have any restrictions like that. We've introduced the restrictions as we solved it kind of in a funny way, but we don't have it from the beginning.
Okay, so we don't have the C.
No,
Okay.
yeah,
So as long as you look at the beginning and there's no square roots or anything.
correct,
Okay.
yeah. So do you guys understand what Adeline's asking?
Yes.
About why we don't just have the top half?
Because R is not restricted.
Yeah, R is not restricted. Now, when we got to this point, it kind of looks like we might have, right, where we have the square root, but we introduced that caveat to what was going on. That really isn't what's going on, so.
Cool.
Okay. Another coordinate system, spherical. Okay, so in the spherical coordinate system, we have a point represented by rho. Rho looks kind of like a P. That is rho. Theta.
Tell me about it.
And phi. You can say phi if you want, but I've always said phi during my math classes, so I'm going to say phi. Okay, rho, theta, phi. It's probably worth mentioning that when I draw my rho to differentiate, I'm going to make it look more like it's got a curly like tail, so it doesn't really look like a P. And phi, when it's in typewritten form, is sometimes written like that. So if you'd rather write your phi like that, you're fine too. Those are the same symbols. So if you prefer, you can do this. That's not a good theta. Let's try that again. Okay. My phis will look a lot like the phis that are written here. My phis look like this when I write them. And then my rho, as I already showed you. Okay. So let's talk about what they are and not just how we're going to draw them. So rho is the distance from P to the origin. Now that's not exactly the same as R, right? Are you with me? R is the distance in the xy plane back to the origin, but rho is a three-dimensional distance back to the origin. Okay? Theta is actually the same angle that we talk about in polar coordinates. So the theta matches. And then phi is the angle between the positive z-axis and the segment we're looking at. So it's a rotational feature as well. Okay? So we're getting the distance from the origin, that's rho. We're getting the two-dimensional distance as it swings around, and then we're getting this distance that it rotates up. Okay? Can you picture it? It's harder to picture than the other one, right? So the angle measure, so if you're in a flat two-dimensional space, this phi is the angle measure that we're lifting to get to my point. Instead of it being a straight up and down distance, it's an angle measure we're getting that rotates up. So you need some equations. The equations are a little bit messier. So x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And you don't get a freebie on z anymore. Z is equal to rho cosine of phi. Okay, the rectangular to spherical is a little bit more direct in terms of it looking like what we've seen before. Rho squared is a three-dimensional kind of a measurement distance, right? So it's x squared plus y squared plus z squared. That should seem reasonable, right? It's the three-dimensional distances like the Pythagorean theorem kind of stuff we looked at. The theta is still y over x. Also makes sense because that theta is still measuring the same thing. They didn't change the variable on us. And the last one is phi. Is that phi or is that rho? It's got to be phi. I can't read my handwriting very well. It's arc cosine of z over the square root of x squared plus y squared plus z squared. That one's the messy piece.
Well, how do we went from z equals z again?
I know. It's true. It's probably worth noting here that there's kind of an easier way to think about this last piece. This piece right here in the denominator is really just rho.
Yeah.
It's just that notationally we don't like to mix things up, right, with rectangular and spherical on the same side. That's why they're not writing it that way. But as you look at that, when we calculate rho, you can just use rho as that denominator. You don't have to redo the whole square root part of it. Okay, same song, second verse. We're going to do the same thing. We're going to take coordinates in rectangular, coordinates in spherical, and swap them. We're going to take equations in rectangular, equations in spherical, and swap them. Okay, we've got our list of equations to work with to do that. So, because the equations are a little messier, you see that there's a little bit more space to work things out on these notes in this part of it. So here's our first one. We're going to do rectangular to spherical. We have 2, 2, and 4 square root 2. And we'll start with rho. So rho squared is 2 squared plus 2 squared plus 4 square root of 2 squared. All right, so what is 4 square root of 2 squared going to be?
32.
32 is it. And then I had my 4 added. I get a total of
Square root
40. So rho is the square root of 40, which simplifies to what?
4 square root of 10.
Close. 2
Two
square root of
square
10. Yeah, just moved a little too quick on that one. Okay, we've got 1/3 of the way there. That's rho. Theta. Well, I use the tangent theta formula. Tangent of theta is y over x. I feel like we've done that one before, or at least one close to it.
This is going to be pi over 4.
It will be. So the tangent of theta is 1, inverse tangent if you wish, but it's a unit circle, nice value too. So theta is equal to pi over 4. Now, technically, it's also 7 pi over 4, right? Like there's other ones we can do, but we're in the right location to do pi over 4. You can see because x is 2, y is 2. They're both positives. We're in quadrant 1. And then we have z. So, I'm sorry, not z, phi. So phi is the arc cosine. Okay, so it's the arc cosine of z, which is 4 square root of 2, over rho, which is 2 square root of 10. So we should clean this up just to see if it's going to be an angle measure that's familiar to us. I don't expect it to because I've got square root of 10 involved. That doesn't really bode well. But it does simplify nicely in there. At least some pieces of it do. The 4 and the 2 reduce. The square root of 2 in the numerator and the square root of 2 in the denominator do. So I end up with 2 over the square root of 5. And if you wanted to rationalize it, obviously you could. That's not going to be an angle measure that's on our unit circle. So at this point, I don't know why that says arc cosine x. That should just say arc cosine. You can take that off. We're going to take the inverse cosine of 2 over square root of 5. And we'll use 3 decimals. I've got 3 decimals in my notes, which probably means that somebody's asking me for 3 decimals in WebAssign or something later on.
0.464.
Do you want us
That's right, yes.
to simplify the radical in the denominator before we start doing?
You don't need to. At that point, I mean, I think before that point, you might have already suspected it's not going to be a nice unit circle value, but at that point where you've got the square root of 5 in the denominator, it's pretty obvious that it's not. So I don't see any purpose in doing so now. 0.464 is what Adeline told me. Is that what you guys have?
Yep.
Okay, yes, and it is in radians. We are doing calculus in radians. I know we briefly detoured with degree measures in one of the sections earlier on. We're not working with degrees in general, though. So our angle or our ordered triple is 2 square root 10, comma pi over 4, comma 0.463. Isn't that a fun ordered triple? Every term is very different than the other, although the last two are both in radians. spherical to rectangular. These equations are a bit more awkward to use. They're less like the other ones we've seen. So we have spherical 12, 3 pi over 4, and pi over 9. So my x is equal to, on my paper, flipped forward, is equal to rho sine phi cosine theta. So the rho is 12. Sine phi, which is my second angle, which is pi over 9. And then cosine of theta, which is 3 pi over 4. Pi over 9 is not a unit circle value. So even though I could certainly get cosine of 3 pi over 4 on a unit circle, I'm going to eventually have to deal with the fact that I've got a pi over 9. So using your calculator at this point is a reasonable step because we're going to have to in the next step if we don't. So go ahead and figure out what you have. And we'll use, again, 3 decimals for all of the stuff in this section. What x value do you get?
Negative 2.902.
Oh, in unison, that was beautiful. Negative 2.902. My y value is rho, which is 12. Sine of phi, so sine of pi over 9. And then cosine, I'm sorry, it's another sign on this one. And then sine of theta, which is 3 pi over 4. Okay, once again, calculator's your friend.
It's the same as x.
It is, except
Positive.
positive. 2.902.
Yep.
I got negative twice. Oh, because I used cosine twice.
That would do it. It's okay, I tried to use cosine on my screen, so that's good. And then our last one is z. Z is equal to rho, 12 again. Cosine of phi, which is pi over 9.
11.276.
Excellent. So our ordered triple is negative 2.902, positive 2.902, and then 11.276. Okay, pretty quick, right? All right, let's do some that are equations that are changing around. So this one's rectangular to spherical. So spherical means I need to have rho, phi, and theta, or some version of those, right, in there. So what are some pieces that you see that you could manipulate with?
I like all the squares, but
Ooh.
we can't just sub it straight in because there's a negative 3 in there also.
We can't, but what could we do to make it work?
You divide it by 1/3.
Nope,
No.
1/3 won't work because we have to divide the other side by 1/3 too.
Yeah.
Like all of them by 1/3.
Can we sub just the x squared and y squared for z squared minus rho squared?
Then we're going to have mixed notation where we have some things in terms of the right things and some are not.
Okay.
Can you, this is gonna be a weird statement, like complete the square or something?
Yes. So what do you have in mind, Adeline?
I didn't get that
It's really
far.
not completing the square, but it is the same kind of feel to it.
But like you factor out the negative 3.
Kind of. Not factoring it though.
Let's just take it out. No, I'm kidding.
Can you just,
Okay.
Well, if you
can
pull out
you
the
just have
negative 3,
4
it's gonna
z
be
squared to both sides?
There you go. Malachi got it. Say it again. What are you going to do?
Just add 4z squared to both sides.
Mm-hmm.
I like it.
Okay, so we're going to have the x squared plus y squared plus z squared that we all were hoping to have on the left. And now we've got 4z squared on the right. So on the left-hand side, there's my rho squared. Now within the same step, though, I need to change out that z squared as well on the other side. So what would I have to do there?
Rho cosine of
Okay, so the 4 is going to stay. And then, say it again, Adeline, rho,
rho cosine of, I already forgot what it's called.
phi.
Phi. I want to call it loop-de-loop, but I know.
Call it loop-to-loop, there you go. Rho cosine phi, and then squared. Okay, so at this point, we have eliminated the mess. Well, we've eliminated the x squared, y squared, z squareds anyway. There's no more rectangular in it. This is still kind of a mess, and we are going to clean it up a little bit, okay? So what we're going to, because I want you to see how nicely it sort of collapses on itself, because it actually really does. So if I were to square this, I would now have 4 rho squared cosine squared of phi, like this. And I can actually divide both sides by rho squared,
Maybe 1.
as long as rho's not 0. If rho's 0, we don't have a three-dimensional shape anyway. So we'd have 1 on the left, and we'd have 4 cosine squared of phi. I've got it written wrong in my notes, but phi on the right. And this is actually something you're familiar with, so I want to do a couple more steps to show you. If you stopped here, it would be okay. But this is actually something you're familiar with. If you were to solve this for phi, we would have cosine of phi equals 1/4 square rooted. Which is 1/2. Where is the cosine value? What do I have? Phi equal to 1/2. Uh-huh.
And negative pi over 3.
At pi over 3 and negative pi over 3. So you may not recognize it at this point. Certainly we could have stopped a couple steps earlier if we didn't care to, but this is actually a cone. So remember, phi is measuring from the xy axis, or the r theta axis, how far up at what angle you go. So if you imagine going up pi over 3, and then rotating it all the way around, right, and going down pi over 3, and rotating it all the way around, that creates a cone. Right? The angle measure is constant, but everything else can vary, right? How far away you are from the x-axis can vary, how far away you are from the origin can vary, those pieces can vary. We actually have a cone here. But I'm comfortable with you at least getting to this point to stop. If you wish to stop there, I'm okay with that. But this is sort of the most cleaned up version that we have for it.
Will WebAssign
I'm not sure what WebAssign will do. You'll have to play with it and see. Yep, Noah?
Could we also have just like looked at the original rectangular equation to identify that that's a
Mhm.
cone?
You could. And if you go back to it, you should be able to recognize it. We've done a cone already today, right? An elliptic cone. This one's not really even elliptic. It's actually, no, it is. It's elliptic because of the 3. It's spheres though, right? They're circles. The x squared and the y squared are circular because their cross sections are circles. It's just not in the same dimension. So it's like sort of like a very squished cone, right? Because the angle is pi over 3 as opposed to being like pi over 4. If the angle were pi over 4, it would be this sort of in the way we normally think about a perfect cone or whatever. But this one's pi over 3. Okay, let's try another one. Here we have rho equals 4 cosine phi. Thoughts?
This would be a little crazy, but you could, if you take, never mind, that won't work.
Okay, let's look at the right-hand side for a moment. This says 4 cosine phi. Do you have any equations that look like a number cosine phi?
Equals thingy cosine.
Yeah,
thingy.
but there's something's missing, right? What's missing for us to actually use that as is?
We need a row on the right side.
We don't have a row on the right-hand side, correct? So why don't we just multiply by row? Okay. Do it to the left, I have to do it to the right, but that's actually kind of nice because what's on the left-hand side now? Rho squared. We have a formula for that, right? And this is now for rho cosine of phi, and we have a formula that says what this is. And we have a formula that says what this is. So what is rho squared?
X squared plus y squared plus b squared.
And what is rho cosine phi?
For z.
Z. You all good with that?
So, I was thinking a more complicated way, what if you put the arc cosine in with the phi?
You get the same thing.
Arc cosine?
Yeah, the arc cosine equation,
Oh.
cosine equals z, yeah, you would get the same thing.
Yeah, you should. Mm-hmm.
That's how I did
Okay, now, if this problem just kind of, left us here, that would be fine. We've changed it. We've got the right variables and such in there, but now it says also we need to sketch. It's not really in the form that we've done for sketching for this, so we're going to manipulate it a little bit. We can move the 4z to the left. So I have x squared plus y squared plus z squared minus 4z. And then somebody already said this on this. I don't know if they saw it ahead of time, but we are going to really complete the square now, not just sort of in our mental mind think it's kind of like the same thing. We really are, plus 4. So we have x squared plus y squared plus z minus 2 squared equals 4. That doesn't look exactly like any of our things, but I think you know what the shape is. Do you?
Ellipsoid.
Ellipsoid?
It's better than an ellipsoid.
A sphere?
It's a sphere. Why is it a sphere instead of an ellipsoid? I mean, technically you can say ellipsoid.
Then we have a radius squared.
Yeah, if we were to divide all the things by 4, they'd all have the same denominator, right? The reason something becomes an ellipse is because one's more elongated than the other, as opposed to being spherical. So this is actually a sphere, and you know where it's centered as well.
0, 0, 2.
Yeah, it's centered at 0, 0, 2. Okay, so if we've gone rectangular to cylindrical and cylindrical to rectangular and spherical to rectangular and spherical to rectangular to spherical, I think I said it all. The only one left to do is to be going back and forth between cylindrical and spherical, and that's our last piece. Okay? So we've already established what the cylindrical and the spherical are. We're just going to establish the relationship between their equations. So spherical to cylindrical, r squared is equal to rho squared sine squared phi. Theta is equal to theta. We talked about that. And z is equal to rho cosine of phi. Which makes sense because that's what the rectangular z was, and the z's are the same when you're doing cylindrical. My rho's and my phis are starting to look too much alike. They're messed up in my notes too. Try to get them better. That's a little bit better there. Okay. The other one, cylindrical to spherical. Rho is equal to the square root of r squared plus z squared. Theta equals theta. Yeah, we get one for free. And phi is arc cosine of z over the square root of r squared plus z squared. But again, notice what that is. That's rho, right? That denominator is rho. Funny fact, this is one of the very few things that I very specifically remember learning in my Calc 3 class when I was in college. Very specific. I don't know why this one sort of rings a bell, but it does. All right, so depending on when you printed your notes might not say that this is problems 8, 9, 10, whatever. They might have the wrong number. It's supposed to say problem 9, I believe, and mine says 8 on my screen, and it says 10 in my notes. So, I split the difference, messed them both up. This is 9. If you printed it later, it's probably right. We're going to convert cylindrical to spherical, okay? Cylindrical into spherical. So we're taking the rho equation, and it's the square root of r squared plus z squared. So r is 4, and z is also 4 here. It's the first and the last. So rho is equal to the square root of
6.
32, which is 4 square root 2. Very good. What's theta? Pi over 4. Yay. And then phi is the arc cosine of z, which is 4, over rho, which is 4 square root 2. Now, this is the point where, like, you should unit circle know this. Your calculator will give you an angle measure, but it's not going to be in terms of pi, right? And we should have this in terms of pi. This is something that we know. This is 1 over square root of 2, but that's otherwise known as square root of 2 over 2. So where is the cosine value equal to the square root of 2 over 2? It is pi over 4. So this is pi over 4 for phi. Oops, phi. So my ordered triple is 4 square root 2, pi over 4, and pi over 4. Are you good with that? Are we good, Noah? You're looking confused.
Yeah, my calculator is different. I'm trying to figure out why. So,
For arc cosine?
yeah.
What is it giving you?
So, I have cosine of pi over 4.
Are you in radians or degrees?
I'm in radians.
Okay.
Yeah.
Cosine of pi over 4.
So cosine of pi over 4 is equivalent to just straight 1 over radical 2.
Okay.
But with 1 radical 2, we still needed to take an arc cosine, right?
Right, because we did cosine, you're doing cosine of it. If you did the cosine of the arc cosine, you'd get back 1 over square root of 2. Let's look at it in a minute. Let me do one more problem and then we'll chat independently. All right, last one. Should be number 10.
Yeah.
Right, are you good?
Yes.
Okay, cool. So we're going to do spherical to cylindrical. So we need to have r theta z when we're done. So we have 4 pi over 18 and pi over 2. So r squared equals rho squared, which is 4 squared. And then the sine squared of pi over 4.
Why doesn't that just simplify to r equals rho sine?
I think that they're trying to make sure that you don't have negatives involved in funny ways.
Okay.
That would be my guess on it. Yeah, but that's a fair question. I have a feeling it has to do with the negatives. R is always, well, I say R can be measured in negatives, but I have a feeling that's why.
Did you change it to be pi over 4 because it's squared? Or?
Because I wrote it down wrong. Because my notes are written down wrong is why. It should say pi over 2, right?
Yes, I was like, the other value
Thank
is
you.
much nicer.
Sorry, pi over 2 is what we want. So 4 squared is 16. What is the sine of pi over 2? 1. And then we'd have sine squared, so we'd have that as being 1 squared, so we'd have 1. So we have 16 here. Yeah, notes. I found like three errors in my notes that you guys didn't even know about, but go ahead. The square root, yes, we're not quite there yet. Thank you,
Oh,
r
okay,
squared.
sorry.
Yeah, and then the r value, you're right, would be 4. Again, we're going to have to make sure, yes, plus or minus, we're going to have to make sure we're in the right coordinates plane to make that work in a minute.
If we get that wrong, how much would you take off?
Not much.
Okay.
All right, theta stays the same. That's my pi over 18, so it's nice to not have to deal with him. And then z is rho cosine of phi, which is pi over 2. And yes, that is 0. Okay, so we need to make sure which r value do we need? We need the positive one. So this ends up being 4 pi over 18 and then 0.
Would it be wrong to not include the 0?
Yes, it is an ordered triple. Yeah, so we are talking about 3-dimensional space. So it is in the plane, right? But it still has to have the 0 to indicate that we knew that. Yeah.